So we look at section 2, data security. We'll talk a little bit on cryptography, but we wouldn't be able to talk much because cryptography itself is a one course. So there's a course called cryptography, called data security, which address data security, which address the cryptography. So we'll look at that briefly, and then authentic digital signature, and then several kind of VPN in different layers. Okay, the cryptography is that you want to encrypt the plain text, and then the encrypted text will be transmitted on the network. And because it's encrypted, so people who intercept the encrypted data would not be able to understand the content. And then the receiver on the other side would use the decryption key to decrypt the data and recover the original plain text. And to do that, the key, encryption key and decryption key, there are two kinds of mechanisms. One is called symmetric key algorithm. The other will be called asymmetric key. When it's symmetric, it means the encryption key and decryption key are the same. Then it's called symmetric. If it's not the same, then it's called asymmetric. And you will see that usually the asymmetric key algorithm is more secure. However, it would take more time to compute. Okay, there is a symmetric key algorithm, and the symmetric key algorithm is easier to compute, but not as secure as the asymmetric key algorithm. So we'll see what is for the symmetric key. It says that the encryption key and decryption key are the same, and what it does is it would encrypt a block of data, say 64-bit data, with a key, say 64-bit data with a 56-bit key. And the encryption procedure is doing this transposition with a 16 iteration, and then do swapping, and then inverse transposition. And the procedures could be better described here, that you have an input, say 64-bit data, and you do initial permutation, and then there's a function that you use, that's the data, and the key, k is the key, and there's a function that you do the operation here, and then you do exclusive OR with the previous iteration, and you do this for 16 times, and then you get back, you got a result. So what it does is this function f with the data and the key, and also you do this 16 iterations. And what is the f? F is actually something like this with the data and the key that combine, doing the exclusive OR, and then doing the parallel operation here, which is called transposition. So essentially, it is iterative. You can summarize the computation as it could be parallel, computed in could be parallel if implemented in hardware. But if implemented in software, you would do one by one. So for example, for this, you would do one by one, and then combine together, and then doing this 16 times. So it's parallel and iterative. And if done in software by CPU, it would take much time. And it's better to be done in hardware because you could go parallel, even though you still need iterative in hardware. And the problem with this kind of symmetric key algorithm, which is the most common algorithm, is called DES. DES. DES is the abbreviation of the data encryption standard developed by IBM. It is possible to break DES easily, but how? Okay, because it's symmetric, so you can do something called plain text attack. Plain text attack, meaning I would input a plain text and get the I will input a plain text and guess a key which is a 56-bit key, and then doing the fit into your DES black box. Now DES is a black box, okay. And then I got the result, and I do the decryption process again. And if I got back the original plain text, then that means the key I put is correct, right? So what I can do is I input a plain text and keep guessing the key, 56-bit key, okay. And then do encryption and then decryption. If I get the original plain text back, then the key I guess is correct. Okay, if not correct, then I change the key. So I can do this kind of plain text attack by keep changing the key until I find my plain text back after encryption and decryption. Okay, and of course that is a very straightforward process, but it takes a long time. It says that with the 56-bit, this could be done. This kind of iterative plain text attack can be done in 4 hours by supercomputer, or by 22 hours by a network of volunteers with many personal computers. Okay, so that means this is not secure if the hackers use this kind of plain text attack, and they will get the key. They will get your key in hours. And the solution is how about run DES 3 times instead of running 16 iteration, you run 48 iteration. So that becomes triple DES. Then the complexity is not just tripled. The complexity grow exponentially. So instead of hours, then now you need years. You need years to do the plain text attack. Okay, so triple DES, although the computation is 3 times, the computation overhead is tripled, but the complexity of doing plain text attack is not tripled. It's exponential growth. So it's not just 3 times safer, but much more than that. So it pays to have a triple overhead by doing 3 times 3 tests, which is called 3 tests, 3 tests, triple tests. Okay, so triple test does this by having the data going through test 3 times, and each time you use a key to do the encryption. So the total length of the key will be if the first key is which key is 64 bits, then the total will be 192 bit key, the total. And in open source implementation 8.1, you see triple test implemented in hardware. Okay, so that's a symmetric key algorithm test. There are some other symmetric key algorithm. The newer one is called AES, which is also used in many VPN products. So it's basically very standard for VPN products to support DES, triple DES, and AES. These are the common encryption symmetric key in algorithms. How about but still the symmetric key algorithm, even though DES, triple DES is much more secure than DES, and AES is also secure and has a reasonable overhead. I mean the computation overhead. But still, if you from the security point of view, they are still subject to plain text attack. As long as the hacker have enough computing resource, they will be able to break the system to guess the key. Okay, so we need another algorithm, another class of algorithms that is even more secure. And that can be achieved by the so-called symmetric key algorithm. And here, the encryption key is not equal to the decryption key. But there's still some principle need to be observed. You encrypt the text and then decrypt the text, it should get back the original text. And it should be difficult to deduce E from D, D from E. And E cannot broken by a chosen plain text attack. Okay, so plain text attack should be difficult to apply here. These are the requirements. So what they come out is an algorithm developed at MIT, which is called RSA, which stands for the last name of 3 inventors. Their last name. And it says this, okay. The encryption key will be N and E, and the decryption key will be N and D. Okay, and the encryption key is usually public key, meaning public available. It's known to everyone. So I've been assigned an encryption key and also a decryption key, but my encryption key is public. Everyone knows this. Everyone knows it's my encryption key. So if someone wants to send a data to me, they would use my encryption key to encrypt the data and send it to me. And then I would use my decryption key to decrypt the data. And the decryption key must be private, must be confidential. Okay, I have my decryption key. So I have two keys. One is encryption, which is public. Everyone know it, and it's announced. So if someone wants to send data to me, they would use the public key, my public key, to encrypt and send the data to me. And then I would use my private key to decrypt. And the private key, the decryption key, which is private, is kept secret. And they do this p to the exponential of e. That's this. And then the result you do a modulation, and mod and modulation. And then you got the cipher data, which is the encrypted data. And then you transmit C. And when the receiver receives C, it would do this. Take C to the order of D, and then modulate the result by N, and then you should get back the result P, which is the original one. And this has been proved by RSA that these two operations will convert the result, convert C back to the original P. And the idea is based on the principle of it's very difficult to factor large numbers. For large numbers, it's very difficult to factor them, factor the number. So based on this principle, so they developed this. Okay, we take one example. So here's an example. Suppose this is a plain text you want to send, and it's transferred into the number, represented in number. So that's the message you want to send. Okay, in numbers, 3, 12, 1, 16. That's the message you want to send. So that's the M. Well, sorry, that's P. P in this formula. So you take that to the exponential of E, which is this. The E, P to the order of E. Now it's M to the order of E. And what is E? It says that the public key, the encryption key, which is the public key, is the exponential to 23. So E is 23. So if you take 3 to the order of 23, you will get this big number. And then you do the modulation of 187. So you will get the result. All the numbers should be smaller than 187. So you got the result here. That's a C. That's the encrypted data that you want to transfer. And then you transfer the data at the receiver. You got this, which is C. And then it take it to the order of what? The secret key. The decryption key here, it says that D is 7. So it take it to the order of 7. Take it to the order of 7. So you got this. And then modulate by 187, which is the same. The private key and public key all have the same 187. So the only number you need to keep it secret will be this, 7. You need to keep it secret. So you take it to the order of 7 and then modulate by 187. That will be 3. And 3 is C in alphabetic. Okay, so you got back the original result. So this column should be the same as this column. So essentially, you have a public key and a private key, and they both have the same N, which is a modulator, 187, but they have different exponential component, 27 and 7. Sorry, 23 and 7. And as you can see, this is the computation is heavy for this one, right? It is going to be heavy because you need to do exponential computation, which is much heavier than modular operations, right? Okay, the modular operation here is fine. That is okay. Modular 187, that's okay. But take it to the order of 7 or take it to the order of 23, that's a lot of computation. So for having that amount of computation, you have a limitation. You can do this on a large number of data, but you can only do it on a small amount of data. A small amount of data, fine, you can do this. But for a large, say I want to do this on a file, 1 megabyte file, that's too much, right? But I want to do this on a small data, which is very small, just several bytes, fine, you can do that. And one common approach is this. You use RSA to protect the symmetric key algorithm. The key used in the symmetric key algorithm. So what I'm doing is, as you will see one example in SSL and SET, what they do is that they they use they want to both sides want to change the symmetric key, and then they can do the key for triple dash. So both sides, this side has chosen a key for triple dash, and it needs to transfer the key to that side so that they would use the same key to do encryption here and then decryption here, right? But how can you transfer the symmetric key, the key to triple dash? How can you transfer and protect the key to triple dash? You use RSA. So what you do is okay, I have a key. The sender here have a key to triple dash. So it would then take the key to triple dash as the input for RSA. So it encrypt the key by its public key, and then transfer. And here it would by its public key. So A wants to send it to B, the key to triple dash. So it take the public key of B to encrypt the key of triple dash, and then send it. And then at B, it would use the private key, its own private key, to decrypt. I mean, its own private key of the RSA private key to decrypt. So it will get the key. So then both sides have the key to triple dash, right? And then they start to do data transfer. So when they are doing data transfer, they use triple dash, which is symmetric. Okay. So in a sense that I only use RSA to encrypt the triple dash key, which is symmetric. Okay. Is it clear? Is it clear? RSA is only used, in this case, is only used to encrypt the key to triple dash. Okay. And I do this in a symmetric way in RSA. And then after both sides have got the key, they would use this key to do triple dash, which is symmetric. Okay. So it's a pair. Every public key and private key is a pair. So you have your public key and private key. And your public key is known to us, but we don't know your private key. So when I want to send data to you, because I know your public key, so I encrypt with the public key, but only you can decrypt. Yeah. So again, RSA is only for very small amount of data. Okay, definitely not for a large data. Okay, so after seeing the encryption, we now see the authentication, which is which is called digital signature. In a sense, why it's called signature? It means that you signed it. I send the data. It's me who sent the data, and I can't deny it. Authentication. It's authorized by me. I authorize this. So authentication, non-repudiation means that I cannot deny. I cannot repudiate. I cannot deny I have sent this. Okay, it's me. I cannot deny. Integrity is not changed. The content is not changed. Okay, so it has its integrity. So the three requirements. And how do we do that? By this, the plain text. So the sender will send the plain text and then attach with the encrypted text. What is that encrypted text? It says that you take the plain text and then input into a hash function. So you will get the hash value, which is a hash value, and then you will take the private key, to encrypt the hash value. That's your encrypted text. So when you send data, you actually append an encrypted hash value, Okay. So when the receiver received this, it got a plain text and also this. But now it needs to check whether the text has been modified or whether it's really sent from that particular source. What it can do to verify is you take this, because it has been encrypted by a private key. So now I decrypt by a public key. So it's the other way around. You decrypt with a public key. You decrypt with a public key. So you got back this. And on the other hand, you take the plain text into the hash function and to get a hash value. So these two values should be the same. If they are not the same, then something must have gone wrong. Either the plain text has been modified or the encrypted hash value has been modified. Okay, so these two must be the same, so that if they are the same, then this digital signature is verified. Okay, so that's a common process for the digital signature at the sender and also at the receiver. And sometimes called message digest, MD. So we have an algorithm called MD5, which is based on this. Okay, even though the plain text, the text itself is not encrypted. In this case, the plain text is not encrypted. It's sent in plain text on the network, but with the encrypted hash values, you still can check whether the data has been changed, whether the data or the encrypted hash value has been changed. And they use a secret key digital signature, the secret key for encryption, and then public key for decryption. Okay, open source implementation 8.2 is on MD5 on the process of encryption and decryption. I mean, the hashed encrypt the hashed and decrypt the hashed values. Okay, next we see the protocols, the protocol issues, where you would have either the VPN. So with encryption and authentication, you still need protocols. These are encryption and decryption are just a mechanism to be done at the source and the sender and the receiver, or the source and the receiver. However, there still needs to be some information carried in the protocol messages. And the protocol could be at a layer 2 or layer 3 or application layer. You will see 2 protocols at layer 2, which is called PPTP, L2TP. They have some small differences. And you will see IPsec, which is at the IP layer. And also there are application layer, which are SSL and SET. They are at the application layer protocols. But what's the difference between putting the encryption and authentication at different layers, or the difference between putting the tunnel, VPN tunnel, at a link layer or network layer or application layer? What is the difference? If you put it at a lower layer, it means that any upper layer transaction or flows will be able to utilize, right? So then if I say, okay, I have a tunnel at layer 2, then all the traffic on this link, I mean on the link, on the link would have encryption and authentication. However, for the link layer, it only covers one link, but it's not end-to-end. It's not end-to-end. So, so you will see if the tunnel is at a lower layer, then the tunnel will be short, but will be able to support more flows. So the coverage of flow will be wide, but the tunnel itself will be short. Okay, if it's at the application layer, very top level, then it's end-to-end. But it only covers this flow, particular flow. Okay, so the covered flow will be less, much less, just one. But it will be long, which means end-to-end. So at if the tunnel is at the application layer, it's going to be end-to-end. And from the client and to the server, from the client to the server. So it gives you the best protection. I mean, in terms of from application's point of view, or the user's point of view, it gives you the best protection. It's end-to-end from the client all the way to the server. It might traverse across many routers, many switches. You don't care. But this is going to be secure, end-to-end. But it only protects this particular flow, this particular client, between this client and this server. It only protects this flow. And if it's the link layer, it's going to be wide. It's going to be cover all the flows on this link. But it's going to be short, only for this link. It's not end-to-end. How about at a network layer? If it's IPsec at an IP layer, it's going to protect, depending on the termination point of your tunnel, IPsec tunnel. it's going to protect this on this tunnel. Perhaps between the gateway of the client side and also the gateway at the server side. But the client is behind and the server is behind the gateway. So here it's not protected. But here between the gateway, these two gateways, it's protected. Okay. Suppose this is I'm a user at a company A. Here there's another user at company B, and between A and B there's a tunnel, and there's a IPsec tunnel. IPsec tunnel established. So it's secure. The data is encrypted and authenticated between the gateway of company A and company B. But inside company A, it's not protected. Inside company B, it's not protected. So if the user is using the IPsec tunnel, and perhaps it uses wireless LAN, and the packet has been sniffed by someone in his company, then it's still not secure, right? Okay, so that's the reality and the difference between different layers. I mean, tunnel at different layers. So we will not look at the PPTP and L2TP. I guess they are not as popular now because they were popular several years ago, but not as popular now. But IPsec is still popular. You would use it, especially for the VPN. I mean the enterprise VPN, and they would have header. They would have header field for encryption and AH and ESP, and also key exchange. So let's just look at the format. Okay. In IPsec, there are two types of tunnel. One is called transport mode tunnel, and the other is called tunnel mode, transport mode and tunnel mode. Let's look at tunnel mode ESP. It means it's encrypted, but this is used when you have a company have multiple sites, site 1 and site 2. Site 1 and site 2, they want to have an IPsec tunnel. They don't care. They don't care inside the company whether it's safe in the company. They don't care, but they care on the internet whether it's safe. So they want to do encryption and authentication between two gateways only, between two gateways, because after the gateway they get into the internet. So what they do is that they encrypt the entire IP packet. So they encrypt the entire IP packet, including the IP header here, and then add the ESP header, and then add another IP header, because the encrypted packet still needs to go on to get into the internet, right? But I have encrypted my IP packet already. So this will be something like this. So this is internet. And this is gateway 1, gateway 2. And inside there's a client A and B here. So here my packet in the IP header here, the source IP address is what? A, and source IP destination IP address will be B. But since they have been encrypted and then sent on the tunnel, so the source address of the IP header here will be what? G1. Destination IP address here will be G2. Right? So this is between the packet between G1 and G2. And it carry packet which is between A and B. But it's encrypted already. Okay, so that's the tunnel mode. And you need the ESP header. You need the ESP header to put some header information and also the encrypted hash values. How about the transport mode? On the transport mode, you don't encrypt the. It's a use when you have this. I'm traveling outside, and it's a hotel, and I'm connected to I'm connecting back to this. And I have no gateway. There's no gateway. So the tunnel is between this and this. So the tunnel is between this. Here the tunnel is between this two, G1 and G2. But now the tunnel is between C and G1. Between C and G1. So it's a transport mode tunnel. And here the header, the IP header here says that the source is C and the destination should be A or G1. A or G1. I think it's source is C, destination is A, but in the ESP header it would say that the termination is at G1. So the tunnel is actually between C and G1. Between C and G1. So that's the transport mode. So either you are in one of the branch office, or you travel around. Okay. And they also need a protocol to do key management, to distribute the key. And there are two protocols, SKIP and IKE, to manage and distribute the keys between the different sites. Okay. Open source implementation 8.3 is on the authentication header and ESP header, encryption standard. ESP stands for encryption standard protocol. Okay, on this, and it's they are implemented as kernel in a kernel module inside. Inside the Linux kernel. Okay, so the third type of kernel tunnel. VPN tunnel is at the application layer. There are two protocol. One is SSL, one is SET. SSL right on top of TCP. So it's here, and it uses exactly what we said. The RSA to do to protect the key to triple dash. So if you see the SSL transaction, within SSL transaction there is a there's a part which is doing RSA to transfer the key to triple dash. So this side, in this case, this side has the key to triple dash, and it's using RSA to protect the key, and then transfer to this side, and then both sides have the key to triple dash, and then they start to transfer the data with triple dash encryption. So that's SSL. So for SSL, it's not between the client and the gateway, between gateways or between client and gateway. It's between client and server. So it's end-to-end. It's end-to-end. The disadvantage is that you can only protect this particular flow. But the advantage is that it's end-to-end. How about set? Okay, set is used in the credit card system. And in the credit card system, because there are multiple parties involved, not just two parties involved in a transaction. In a credit card transaction, there are many parties involved, not just two. So SSL is suitable when only two parties involved, client and the server. But if you want to use SSL in the credit card system, which have more than two parties involved, then there are problems. The problem is, what if the server is not reliable or accountable? If the server might be using the client credit card illegally. So if the server is not trustworthy, it's a problem. So we need another party who would check against the server. In the credit card transaction example, the server is the shops. The shops you purchase something. Okay. So the shops might not be accountable. Then you need another party to check against the shops. Okay. And another example, another problem with SSL is the client might not be accountable either. Okay. So the client might be sending unauthorized credit card. So you need another party which will check against the client. So either the client or the server needs to be checked by another party. So then it will come up with a structure like this. I didn't put this on the book because it's too complicated. So here's the card holder. That's you. You're the card holder, for example. And then that's a merchant, which is a server, a shop, a restaurant, where you buy something, you spend the money. And and there's a bank, the bank that issued the credit card. The bank that issued the credit card. And here is the Visa, MasterCard, American Express, the credit card company. Okay, the credit card company say, okay, the credit card can be issued by Bank of Taiwan, Bank of America. So, but behind there's a credit card company, Visa, MasterCard, American Express, who maintain the accounting. I mean, who maintain the account information. Okay, so it involves multiple parties, and the transaction is complicated from 1 to 12. So you can imagine that they distribute the responsibility among many parties, and those parties, they check against each other. So in a sense, set expand SSL from two parties, from a two-party protocol to multi-party protocols. Okay, and but for the authentication and encryption mechanism, they are the same. They are the same. But it's just the protocol. The protocol and the involved party are different. Before we get to the okay, let me check. Okay, we have the video. We haven't got the video for last week. Last week is not available yet, so I'm going to ask whether they can post the video last week sooner. And homework number 7, which would include chapter 7 and chapter 8, 2 hands-on totally, and 5 written, and it due next week right before the final in the class. Okay, and as usual, as midterm, we would distribute the solution right in the final exam, so you will see what's the correct answer. And also, the final exam is on next week, but it's only 2 hours, so it's not 3 hours, 2 hour final exam from 3:30 to 5:30. And we will cover from chapter 4.2 to chapter 8. And it's as midterm, it's open book. And you can bring any printed material, but no electronic devices. In the meanwhile, two students just asked me in chapter 7 in the hands-on written in the written exercise number 13. There's a typo in the book. It should be 2210-4. 2210-4. Not in the book. It missed 2 here. Just 2, 10, and 4. So 4 packet arrival, and the length should be 4 entry here. But the book just had 3 entries, so it missed a 1, 2 here. So it should be 2, 2, 10, 4.